Hello, I would like to welcome you to the fourth lecture of 2FH3. In this lecture, we'll start to discuss differential elements in Cartesian, cylindrical, and spherical coordinates, line integrals, surface integrals, and volume integrals. We cover material from chapter 3, pages 57 to 67. A very important concept in the area of vector calculus is the concept of differential element. And I will start by illustrating that in Cartesian coordinates. Here we have a differential element. We have a point S, which is this point shown here, and a point B, which is shown here. In moving from S to B, we can define this tiny differential length element. In moving from these from S to B, we actually increase x by dx, we increase y by dy, we increase z by dz. And then we define this differential element, which is shown in this figure. This differential element has 6 surfaces, or 6 differential surfaces. The first one is the front one, which is this one here. And usually we take the unit normal to the surface, or we define actually the area of the element as a vector whose direction is the direction of the normal to the surface. For example, the element here to the front, it has dimensions dz in this direction. So there is this dz, and in this dimension here it has dimensions dx, and it's pointing in the direction of y. So we call that the area of this element is dx dz, but it's pointing in the y direction. The element to the side here, whose edges or whose vertices are a, b, c, and d, has dimensions dy and dz, and its normal is pointing in this direction, which is the x direction. So this differential element defines 6 surfaces. It defines one differential volume, because the volume of that tiny differential element is dx, dy, and dz. Ds is the product of dx, dy, dz. So it's very important to understand this in Cartesian coordinates. When you move from a point to a nearby point, we are actually changing x by dx, we're changing y by dy, we're changing z by dz, we're creating what we call a length element. In this case, in Cartesian coordinates, this will correspond to dx, ax, dy, ay, dz, az, and this is here in this figure is the differential element pointing from S to B. We define for this element 6 faces. Two of them are one is actually, let's be more specific. One is pointing in the x direction. The other one in the back is pointing in the minus x direction. One to the side is pointing in the y direction. The other one to the other side here in the back is pointing in the minus y direction. And then the top one is pointing in the z direction. And then the bottom one is pointing to the minus z direction. So we define 6 surfaces, 6 differential surfaces. And as I said, in electromagnetics and many other fields of science, we define the vector, the area vector, as a vector whose direction is normal to the area and whose value is equal to the value of the area. So we'll be using this over and over again in this course. So, as I explained in Cartesian coordinates, we have differential surfaces. I'm just showing you here the 3 pointing in the positive coordinate directions. So there is something called ds in the x direction. The area vector pointing in the x direction is equal. Its value is dy dz, but it's normal. The normal to that surface, which is really the direction of the area vector, is in the ax direction. The second one, which is the dsy area vector, it has magnitude of dx dz, and it's pointing in the y direction. As we agreed, the area vector will have the direction of the normal to the area. The last one is the dsz vector, the area vector in the z direction. It has a magnitude of dx dy and it's pointing in z direction. I'm showing you only 3, but the differential element we had 6 faces, because there is another differential element whose magnitude is dy and dz, but it's pointing in the minus ax direction. There is another one whose magnitude is dx dz, but it's pointing in the opposite direction here, so it's pointing in the minus ay direction. And there is the last one, it has also magnitude dx dy, but it's pointing in the az direction, in the negative az direction. So we'll know the benefit of all these elements very soon when we start to talk about line integrals, surface integrals, and volume integrals. And just remember the differential element that I explained to you earlier will also define what we call a differential volume. It is the product of all these coordinates, so it's equal to dx, dy, and dz. I intentionally started by explaining the Cartesian case because it is the easiest one to understand, and it's where most students are familiar with it. But really, we can define the same thing for cylindrical and spherical coordinate systems. So here we can see what we call the differential element for cylindrical coordinate systems. So you can see it's the same thing. We move from a point R, which is this one here, to a point A, which is this one here. So we define a length vector pointing from this one to this one here, from R to A. And going from R to A, we increase rho by d rho. So you can see there is an increase here of d rho. This is d rho here. And we increase phi by d phi. So you can see this angle here, this angle, I'll just try to draw it carefully. This angle here is actually d phi. Okay, this is d phi, and we increase z by dz, so this height here is equal to dz. So in moving from B to A, we perturb all three coordinates, and this creates this differential element here. Again, we can define a corresponding length vector, but one important thing to realize that's different here from Cartesian coordinates is that whenever you have an angle, the length corresponding to an angle is equal to rho multiplied by the perturbation of that angle, or the length, the radius multiplied by the perturbation of that angle. For example, here, if I take a look at the lower figure, this length here, this corresponds to a perturbation of d phi, but its length is actually equal to rho d phi. Okay, so this length here is equal to rho d phi. For the z and rho, it's fine, it's the same thing because these are not angles. Okay, so if I try to focus on I try to actually magnify that unit differential element in the picture to the bottom. So you can see here we have the same thing. We have 6 surfaces, and we have one volume, one differential volume. So 6 differential surfaces and 1 differential volume. Of course, when d rho, d phi, and dz are extremely small, the curvature does not make a difference. So we can say that the area of this surface here is equal to rho d phi dz, while the area of the surface here to the side, if I can draw it properly here, is equal to d rho multiplied by dz. The area of the top surface, which is shown here, this one here, is equal to rho d phi multiplied by d rho. Of course, this one is pointing, the area of this one is pointing in the z direction. The area of this one is pointing in the rho direction. The area of this one is pointing in the minus phi direction. Remember, phi is in direction of increase of phi. So this is minus phi. The positive phi is the one behind that, the one behind this one. So, as I said, this element, again, if you move from one point to another, from point R to a point which is very close to it, point A, so it's a differential element, we perturb rho by d rho, we perturb phi by d phi, we perturb z by dz. The length perturbation corresponding to d phi, as I stressed earlier, is rho d phi. And this is coming from the fact that the arc corresponding to an angle of d phi, a small angle d phi, is equal to the radius multiplied by d phi. While for dz and d rho, because they are length, there is no problem. So the unit vector pointing, the length vector pointing from R to A, it's not a unit vector, it's a length vector pointing from R to A, is given by this length vector here. It is d rho in the rho direction, rho d phi in the phi direction, and dz in the z direction. And we, as I said, we define 6 differential surfaces and 1 differential volume. Of course, here the volume of this element is not that difficult to see. If you multiply all the edges, it will give you rho d phi dz. This is the differential element, differential volume element that we need. So we have 6 differential surfaces and we have 1 differential volume. So this figure expands each one of these surfaces, and we show the main ones. So here, if we only consider the front area, you can see this arc here has a length of rho d phi. This arc here has a length of dz. Then this whole area is an area which has a value of rho d phi dz. But it's pointing in the rho direction. So this will give you the area vector, or the differential area vector in the rho direction. The same thing if you take one of the side edges. So you can see here this length here is equal to d rho. Here phi is a constant. Phi is a constant, so it is in a plane normal to the xy plane. So here this is the element that we have. This one here is d rho. This one here is dz. The normal in the direction of increase of phi is a phi. So this is a differential surface element. It has a magnitude of d rho dz, and it's pointing the phi direction. The last one is the top one, which I don't like the way it's drawn here. If I were to draw it, I will draw it a little bit differently. It will look something like this. Okay, so here I'm looking at the differential element from a little bit higher angle. So this one here is rho d phi, and this one here is d rho, and the normal to this one is indeed in the z direction, so it's az. So the last differential area vector is this one here. It is equal rho d phi in the z direction. And remember, the differential volume that we define in cylindrical coordinates has volume. You multiply all the edges, you ignore the curvature because you assume these are tiny differential elements, the differential dimensions. So it's equal rho d phi dz. The same thing can be done for spherical coordinates. So you can see here I'm defining 2 points, P and Q. So this is point B here, and this point Q. You notice that when I move from B to Q, I increase R by a length of dr. So R was increased by dr. I increased theta by d theta. So you can see there is an increase here in theta, this angle here, this tiny angle here. And I increased phi by d phi, which is this angle here. So in moving from B to Q, again we can define a differential length. So it's pointing from P to Q, okay, as shown here. And remember, the arc corresponding to an angle is equal to the radius of this, to the radius multiplied by the d of that angle, the differential value of that angle. So here we have a number of edges. This one, the one in the r direction, is the easiest. This is equal to dr. There is no problem. I made the change in the r direction. It's fine. The arc in the theta direction, this arc is also not that bad because the radius here is r. And if you perturb by d theta, then the length of that dimension or that edge is r d theta. The tricky one is the one in the phi direction, which is this one here. Because the radius of this one is actually rho. And if you remember, rho is the rho normal to the z-axis, to the point, and rho is equal to r sine theta. So the radius, so this edge here has dimensions r sine theta d phi, which is actually rho d phi. So now we're able, in the same way we did it in Cartesian coordinate systems, the cylindrical coordinate systems, to define a differential element. This differential element has 6 faces. Each face has its own angle and its own direction. We're able to define a differential length, dl is equal to dr ar r d theta a theta and r sine theta d phi a phi. And remember where all these r came from, because the angle, the length corresponding to a differential angle is equal to that differential angle multiplied by the radius. and the radius for the theta case is equal to r as shown here, while the radius for the phi case is rho, which is r sine theta. Of course, they define also differential volume. And if you multiply the length of this differential element, so you get here, you get the differential volume, r squared sine theta dr d theta d phi. This is the volume of that differential element. So it's pretty much the same that we had in other coordinates, but we have here two differential angles. I decided to use this other figure for spherical coordinates because it shows in a more clearer way all the dimensions when you move from one point. So if I call this point here, this will be by point B, and this one here I will call it point Q, where I increase r by dr, theta by d theta, and phi by d phi. And here you can see all the angles that we have. And again, if I take a look at the top surface, this one here, if I take a look at this surface here, this surface is pointing in the r direction. Okay, so it's AR, and its area is equal to r d theta here, r sine theta d phi here. So it's equal to r squared sine theta d phi, and it's pointing in the r direction. Now, if I take one other area, maybe the one to the side here, this one here, so this small rectangular shaped area, this one has dimensions dr here, this is dr, and this one here is r d theta. So it's r d theta dr. This is the area, and this one here, the normal to this one is in actually the minus phi direction. So maybe I should, the other one, the opposite to it, is pointing in the phi direction, and so on. So we have really three surfaces. Maybe I should stress on the other one as well. The third surface is the one I'm trying to draw for you here. This is the third surface, and this one here is pointing indeed in the theta direction. This is a theta. And this one has dimensions of dr in one side and the r sine theta d phi in the other side. So in general, we have 6 faces in the same way we had in other cases. So these are the 3 of the main differential surfaces that we have. The one corresponding to the r direction, it's r squared sine theta d phi. Remember that the arc dimension in the phi direction here is r sine theta d phi because it corresponds to rho, while the arc dimension, the length in the theta direction, is equal to r d theta, which is this one here. Okay. The same thing if you try to get the unit vector pointing in the theta direction. Again, this is a perturbation in the r direction, so this is the direction of r. This is a perturbation in the phi direction, so here theta is kept constant, and you can see the unit area is normal, or the unit normal is in the theta direction. So this is the unit vector in the direction of phi, and direction of theta. Actually, again, I'm repeating, I should correct that. It's not a unit vector, it's an area vector. It's a differential area vector, and the direction of theta, it's r sine theta d phi dr. So this is its magnitude, and here, of course, there is a comma. This comma should go, it does not exist. This is all in the theta direction. The last one, of course, in the phi, and in the phi we have a length in the r direction, and we have the length in the theta direction, which is r d theta. This is the arc corresponding to the angle d theta, and this is all in the direction of constant phi. And of course, I'm showing only 3, but there are actually another 3 in the one in the minus er direction, one is the minus a theta direction, and one is the minus a phi direction, because we have 6 differential faces. Of course, there is only one differential volume, and its value is given here. You simply multiply all the edges, multiply dr by r d theta by r sine theta d phi, and you end up getting r squared sine theta dr d theta d phi. So why do we bother with all these differential lengths, differential surfaces, and differential volumes? You will see in a second we need them in a number of type of integrals used very often in electromagnetics. We use them in line integrals, we use them in surface integrals, and we use them in volume integrals. So a line integral, I will start by explaining what's a line integral by giving a motivation for it. We know from our previous study that if you have a force F and it exerts work in moving from one point to another, then what you have to do, you usually say that we multiply F. If this is F, this is the direction of movement, we multiply F by dl. This is if they are in the same direction. If they are not in the same direction, you have to project F in the direction of L. So this is equivalent to taking the dot product between F and the vector dl. So this can be defined as a vector, and F can be defined as a vector. However, if your contour as shown here, it has some curvature and so on, numerically how we do it, we divide our element into, or our contour into elements. So this is the first element dl1, this is the second element dl2, and then you have here dl3, you have dl4, you have dl5, and so on, and then the ith element dli, and then you go to the very last element, which will be, say, dln. And then you do a dot product between F at the center of every element with the direction of that element. So as shown here, you try to find the work exerted by this force along this small length vector. So and you sum over all the elements. And of course, if F is changing from one point to another, you calculate F at the center of the element. This is why I call it here Fi. So Fi is the value of the vector at the center of the element. dli is the length of the element, and cosine theta I is the angle between the force and the unit, the length or the length vector at this point. So this is really a definition of work. And this is how actually we do it numerically. If I ask you to do, and you'll be doing this actually in the MATLAB assignments, I ask you to calculate the potential difference between one point on another. Then what you have to do, you have to find the work done by the electric field. And then you divide your contour into small segments, and then you sum the contribution coming from each segment. Now, if we take the number of segments, n, so here we said we have up to n segments. If we take n to be extremely large, goes to infinity, then every element becomes a differential element, and the summation becomes an integral, and we end up with what's called line integral. It's the integral over the contour from the start of the contour to the end of the contour of f dot dl. So you try to find the expression for dl, and you do the dot product, and then the answer will give you the work done by this force. And again, you should know why do we need to use this. You will see very soon that the potential difference, what we call in your circuits voltage difference, is nothing but the negative of the work done by the electric field. So this will be used very soon in our electrostatics part. Best way to illustrate line integrals is to show an example. So I'll show an example here. We have a field. You can think of it as an electric field. It has two components, xy ax minus 2x ay. We would like to evaluate the scalar line integral. We want to integrate. You find the work done by E over the contour from A to B as shown here, where A and B are 2 points on a circle whose radius is 3. We go from phi equal to 0 to phi equal to pi over 2. We want to do this integral, this line integral, or this work calculation using Cartesian and cylindrical coordinates. So we'd like to see how this can be done. Of course, in Cartesian coordinates, we defined what's dl. dl is equal to dx ax plus dy ay plus dz az. So we can immediately start multiply E, which has two components, only x and y, by dl, which has dx, ax, and ay in the EZ components, and then start to solve the problem. If you do the dot product, you'll see there is no z component here for the vector E. This is why dz will give you 0. dx will be multiplying this part, and dy will be multiplying this part. So we end up with two integrals as shown here in this step. One over the contour over this quarter of a circle from A to B over x, and the other one again over the same quarter of a circle from A to B dy. Of course, if you are integrating relative to x, you have to get rid of y. If you are integrating relative to y, you have to get rid of x. And this will come from the equation of the contour. We know that the contour is a circle, and the equation of this circle is x squared plus y squared is equal to 9. And it is in the positive part. So I can simply say in this positive part is x is equal to square root 9 minus y squared. And I can say that y is equal to square root 9 minus x squared as shown in these two integrals. Now, a word of warning, notice that I put the limits of the integral of x from 3 to 0 because we are moving from point A to B, and A has an x of 3 while B has an x of 0. While for the other integral, in moving from A to B, the first point has a y of 0 here and has a y of 3 at the end. So this is why the order of these integrals is extremely important. What remains is simply to carry out these two integrals to get the value of the work done by this field. The first integral is easy to calculate because the derivative of x squared is equal to x. So this looks like it's a bracket that was differentiated. So the bracket now has a power of 1/2. So it becomes power 3 over 2, and then you multiply by 2 over 3. While this second integral here relative to y is not very obvious, it's one of those integrals you can find them from the tables. And if I give you such a problem, I will give you the expression for this integral. If you carry out these two integrals, the first one is pretty straightforward. It will give you the bracket raised to the power 3 over 2, and then you multiply by 2 over 3, and there is a negative sign because you're integrating minus x squared. The other one here, it has a formula. Actually, it will give you y square root 9 minus y squared plus 9 inverse sine of y over 3. So this is inverse sine of y over 3, and this all. The first one is between 3 and 0, the second one between 0 and 3. If you substitute for the upper and lower limits, you'll see that the first integral will give you minus 9, and the second integral for the sine part, when you put y equal to 3, will give you pi over 2. So it's minus 9 multiplied by pi over 2. So the answer for this question is 9 multiplied by 1 plus pi over 2. In order to repeat the same problem using cylindrical coordinates, it's not that difficult because it should give you exactly the same answer regardless of the coordinate you do it in. But just to keep in mind, when you have this arc that you have, this quarter of a circle is pointing in the phi direction. So the dl in the direction of that arc is equal to rho d phi e phi, as I explained earlier. Of course, you can put all you can put a general dl, but you should realize you are not changing rho, you are not changing z. Then d rho is 0 and dz is 0. So and of course, when you do the integral in the cylindrical coordinates, you have to convert first your vector to cylindrical coordinates, and this is what I'll be doing in the next slide. So we start solving by transforming our vector from Cartesian coordinates to cylindrical coordinates. And because I know that my contour has only a phi component, the vector dl is equal to rho d phi e phi, because I'm moving on a circle. I'm not changing rho, I'm not changing z. This is why I will need only e phi, so I will calculate only the second rho. So I know e phi is equal to minus sine phi multiplied by xy. I will replace x by rho cosine phi. I will replace y by y sine phi, and this will give me rho squared cosine phi sine phi. The same thing I will do for the second term. So the second term here has cosine phi multiplying minus 2x. I will replace x by rho cosine phi. This will give me minus 2 rho cosine squared phi. So if you organize things, this is the value of e phi that you are going to be getting. Okay, so this is how this is a phi component. This is not the full vector. I don't really care about the rho component because it does not exert any work, because rho is normal, the e rho is normal to the direction of the contour, so it does not really put any work, and I would like you to verify that. And we carry out the integral again in cylindrical coordinates. We integrate e dot dl. Remember, dl has only one component. It is equal to 3 d phi a phi, because we are integrating over an arc of a circle. d rho is 0, dz is 0. So when you dot product this dl with E, you end up only with the phi component multiplying 3d phi, and you integrate this from A to B. Remember, from integrating over this quarter of a circle, phi here is equal at the starting point is equal to 0, while phi here is equal to pi over 2. Remember, phi is the angle measured from the x-axis. So if you do the integral, you substitute for E phi, you multiply everything by 3. The integration of this part is easy because the integral of psi squared cosine phi will give you sine cubed phi divided by 3. The integration of this one, we first convert cosine squared phi into 1/2 1 plus cosine 2 phi, and then we integrate it. So here you can see there is a rho in these two integrals, but over the contour, it's rho is a constant because it is part of a circle, and rho is equal to 3. So this is why I replaced the rho squared by 9. So here you end up having minus 27 after multiplying with 3. And in this part, 2 rho here will give you minus 6. You multiply by 3, so it gives minus 18. The first integral can be done very easily. It gives you sine cubed over 3. The second one, you have to you convert cosine squared phi into 1/2 1 plus cosine 2 phi. Do this integral. The integral here, you put the upper limit. Upper limit will give you minus 9. Lower limit will give you 0. For the other one, as I said, we replace the cosine squared by 1/2 1 plus cosine 2 phi. So end up here 18 over 2 give you 9. And then the last part, you integrate 1 will give you phi. You integrate cosine 2 phi will give you 1/2 sine 2 phi. You substitute between 0 and pi over 2, and if you do this substitution, you will see you get only pi over 2 from the phi term, and everything else is 0. So this is the answer that you get, and this is exactly the same answer we got from Cartesian coordinates. And as I said before, a vector is the same vector whether you express it in Cartesian, cylindrical, spherical. A dot product is the same dot product whether you express it in cylindrical, Cartesian, or spherical. And a line integral, which is work, is the same value whether you do it in the Cartesian coordinates or cylindrical coordinates, spherical coordinates.